Okay, good evening. I think we can go ahead and get started. Welcome to our Unit 4 live chat. Tonight, we'll talk about some issues around database administration and all things that are related to that. So we'll go ahead and jump right in. First, we're going to talk about security and administration transparencies. Database security, as you are all aware, data is a very valuable resource that has to be strictly controlled and managed as with any other corporate resource that your company may have. Part or all of the corporate data may have some strategic importance and therefore needs to be kept secure and confidential. There are mechanisms in place that protect the database against any intentional or accidental threats. Security considerations do not only apply to the data held in the database. Breaches of security may also affect other parts of your system, which may in turn then infect your database. Some involve some measures to help avoid theft and fraud or loss of confidentiality or secrecy of your data, loss of privacy, integrity, and the availability of your data. A threat defined as any situation or event, whether it's intentional or unintentional, that will somehow adversely affect your system and consequently your organization as a whole. These are just some examples of some threats to computer systems. As you can see, they have the different components marked here. There's hardware, communication networks, users, some programmers, database administrators, and of course the database and the DBMS and application software that attach to the database and sort and save and report the data. So this is the area we're concerned about. You may have unauthorized amendment or copying of your data, theft of your data, or corruption due to some sort of power loss or surge. This is a typical multi-user computer environment. You have a remote client, right, using encryption, going through some insecure external network, for example, the internet. And then there's another layer of encryption on the other end of that connection, which then you probably flow through some sort of firewall. And then eventually you make your way into the DBMS server, which has programs and policies in place that help with authentication, authorization, and access control, even for your local clients, which may be inside your company, before you actually get to the actual database itself. So there are several layers in place before you actually get to the database, and all of those layers must be protected. Some countermeasures for computer-based controls are concerned with actual physical controls to administrative procedures, and it includes the authorization or access controls, views, backup and recovery of the data in the database, your database's integrity, encryption, and RAID technology, which we'll go into, and we'll discuss each of these in some of the upcoming slides. So authorization is simply the granting of a right or privilege, which enables a subject or user to legitimately have access to a system or a systems object. It's a mechanism that determines whether a user is who he or she claims to be. That's authorization. Access control is a little bit different. It's based on the granting and revoking of privileges. A privilege allows you, the user, to create or access, that is, read, write, or modify some sort of database object, like a relation, a view, index, table data, or to run certain DBMS utilities, like backup and recovery processes, right, or replicating the database. Privilege are granted to users accomplishing tasks required for your specific job. So not everybody will have full rights to your database at any one time. Most DBMS systems provide an approach which is called discretionary access control, or DAC. The SQL standard supports DAC through the grant and revoke commands in SQL. The grant command gives privileges, as you may assume by the name, and the revoke, of course, command takes away any privileges that you may have. Those are usually controlled by the database administrator or the data administrator. They'll use those commands to grant and revoke privileges to users, or more likely to user groups, using your network security. Your network security will have user groups, and people can add it to those groups, and then they can give access to groups instead of individual users. It's a little bit easier and a lot simpler to control. While this DAC is effective, it does have some certain weaknesses. In particular, an unauthorized user can trick an authorized user into disclosing sensitive data. Don't ask me how you trick somebody to do that, but evidently it's possible. An additional approach is required, which is called mandatory access control. This DAC is based on a system-wide policy that can't be changed by individual users. And then every database object is assigned a specific security class, right? And each user is assigned a clearance for that class. And then the rules are imposed on reading and writing of database objects by those users. So there's a whole separate layer of security within the database itself. This DAC determines whether a user can read or write an object based on the rules that involve the security level of the object and the clearance of that user. So it can get quite complex. These rules ensure that sensitive data can never be passed on to another data without the necessary clearance. Of course, the SQL standard does not include support for this MAC. A view, which we might have talked about in a few of the other live chats, is a dynamic result of one or more relational operations operating on the base relation or table. Remember, a relation in the database is a table, to produce another relation or table. A view is a virtual relation. It doesn't actually exist in the database, but is produced upon request by a particular user at the time of the request. Backup is simply, you may be familiar with backups and restoring of data. You probably do it to your own home PC, possibly. If not, it's a good practice to get into. Windows has a built-in backup, so you can use that. It's the process of periodically taking a copy of the database on a log file and possibly some programs to some sort of offline storage media. Journaling is this process of keeping and maintaining a log file or a journal of all the changes that have been made to the database to enable effective recovery in the event of any failures. Integrity, it prevents data from becoming invalid and hence gives misleading or incorrect results. Encryption, which you may be familiar with, is a process of encoding the data by a special algorithm that renders the data unreadable by any program without the decryption key. I think most organizations that allow users to work from home and they provide a laptop computer, your laptop computer, the disk drive is probably encrypted, the contents on it. So if you were to lose your computer, people can't access the sensitive data you may have from your work. We'll go into RAID. We'll talk about some different RAID levels. RAID stands for the Redundant Array of Independent Disks technology. If you've heard of that before, if not, it's good to look into. There's hardware that the database management system is running on has to be fault tolerant, meaning that the DBMS should continue to operate even if one of the hardware components fails. They suggest having redundant components that can be seamlessly integrated into working system, whether there is one or more component failures. The main hardware components that should be fault tolerant include your disk drive, your disk controllers, your CPU, power supply, and cooling fans. You don't want those items to fail. If they do, it could cause your whole system to crash. So you want to make sure you have a practice in place. So you have redundant components for all those items. So if one, in the case one fails, you have another that can pick up the backup. Disk drives, of course, are the most vulnerable components with the shortest times between failure of any of the hardware components because you're consistently reading and writing to a disk drive, so they fail faster. One solution here is to provide a large disk array comprising an arrangement of several independent disks that are organized to improve reliability and at the same time increase your performance. Performance is increased through what's called data striping. The data is segmented into equal sized partitions, which are called the striping units, and they are transparently distributed across multiple disk drives. Reliability is improved through storing redundant information across the disks using a parity scheme or an error correcting scheme. And in certain RAID levels, they do that. We'll talk about these different RAID levels. There are several different disk configurations, which are called RAID levels. RAID 0, which is non-redundant, all the way up to RAID 6, P plus Q redundancy. There may be higher levels now. As you get higher in the levels, it gets more complicated. They add those bit parity bits and all that other stuff into there to make it a little bit more reliable and faster to improve performance. So we'll go through each of these, I think up to block 5. And we'll talk a little bit about them and we'll show the comparisons between the two. So between RAID 0, which remember was RAID 0 is non-redundant and RAID 1 is mirrored. In a RAID 1 non-redundant array, you just have in our example here, in these examples, we have 4 disks in our disk array. You could possibly have more. And this one, it just does parallel writes. It writes the data 1, 2, 3, 4 in sequence across the different disk drives. And you do parallel reads. There's no replication of the data like there are when you get to RAID 1. RAID 1 is parallel writes. It does mirrored writes. So disk 1 and 2 in our example both contain the same data. It writes the same data to both drives, and disk 3 and 4 have the data written to the same drives. So if disk 1 and 4 failed, you'd still be able to operate your database while being able to swap out those 2 bad drives and then replacing them with a new one. And then it continues to write the parallel writes and mirroring the disk. So it's a very simple and basic way to do the RAID levels. But now we get a little bit more complicated with RAID level 2 and 3. Right, RAID level 2 has a memory style error correcting code, MSEC code, written to disks 3 and 4 in our example, and the data is written to disk 1 and disk 2. And in RAID 3, we're doing each write spans all the drives in both of these instances, right? So in RAID 3, with a bit interleave parity bit, it writes that bit interleave parity bit to the disk 4. So a data for 1 gets written to disk 1, 2, and 3 at different segments, and then that parity bit gets written to the 4th one. In case of a disk failure, it can recreate it. And then 4 or 5, I think this is the last one for the disks for the RAID levels we'll go through. 4 is a block interleave parity bit. As you can see, it writes it to this drive. It shows there are parallel writes from these drives over and then down 1, 2, and 3. And 5 writes parallel. It writes the block IDP bit to the parallel drive, and the data is written across the drives in the sequence that it shows with the arrows. DBMS and web security. So the internet communication relies on, as you may be aware, TCP/IP as your underlying protocol. However, this protocol and HTTP were not designed with security in mind. So without special hardware, any internet traffic travels in the clear, and anyone who monitors their traffic can read it. So you must ensure while transmitting information over internet that 1, it's inaccessible to anyone but the sender and receiver. It maintains its privacy. 2, that it's not changed during that transmission and keeps its integrity. 3, the receiver can be sure it came from the sender. It's authenticated. The sender can be sure the receiver is genuine. There's non-fabrication. And then the sender cannot deny he or she sent it, meaning that there's non-repudiation. You can't deny you sent it. Some measures include using proxy servers, firewalls, message digest algorithms, and digital signatures, some digital certificates, Kerberos, secure socket layer SSL, and secure HTTP, a secure electronic transaction or SET, and secure transaction technology SST, and then Java or ActiveX security are all ways to manage the database management system over the web. We'll talk about one of those, which is the secure electronic transaction, since we're building a retail store, right? So this is probably a good one to talk about. It's an open interoperable standard for processing credit card transactions over the internet. It was created jointly by Netscape, Microsoft, Visa, MasterCard, GET, SAIC, TerraSystems, and VeriSign. It is split in a way that the merchant has access to the information regarding item purchase, but not what payment information the user is using. So buying over line, they never see your credit card information. It works in this way, in this manner, with this little diagram that I have here. The steps are numbered, starting with the customer initiating the transaction by sending in the order form and assigned encrypted authorization. The merchant can't access that credit card number because it's encrypted. The merchant passes that authorization on authorization to the bank, who can then decrypt it and sees the credit card number. It can also check the signature with the certificate to make sure that it's coming from the correct person, right? A correct authorized user of that card. The acquiring bank checks with the card issuer to see if the card's okay. If the card is okay, the card issuer authorizes and signs that transaction. The bank then authorizes the merchant and signs that transaction for the merchant. The customer gets your goods and your receipt in the mail. The merchant asks to capture the transaction and get paid. Merchant gets his money paid according to his contract. And then finally, you, the user, get your monthly bill from the card issuer. So that's just a really good way to show this, how this process works. So now we're talking about some transaction management, because in IP4, you have to develop a transaction management plan. So some of this information may be helpful for that process. A transaction defined is simply an action or a series of actions that are carried out by a user or an application which reads or updates contents of a database itself. It's a logical unit of work on the database. The appellation program is a series of transactions with non-database processing in between them. And it certainly transforms your database from one consistent state to another. Although consistency may be violated during the transactions, and we'll go into all of that. This is an example of what a transaction might look like. Notice transaction A, they're reading some data, staff number, where it's equals to whatever value they entered and that person's salary. They're taking that salary and then multiplying it by 1.1 to give the person a raise. So then they're going to write the new salary for that staff member person. In transaction B, looks like they're deleting a record for all property for rent records. So they're going to read property numbers. If the staff number equals a certain value, then the staff number equals new staff number, and they write the property number and end the transaction. So that's just an example of essentially pseudocode for transactions that occur against the database. Transaction support can either have one or two outcomes. You're going to either be success or failure, right? The transaction commits to the database and reaches a new consistent date, meaning it was successful. A failure means the transaction is aborted. The database must be restored to a consistent state before it started. Such a transaction is considered to be called rolled back or undone, so that the changes aren't effective in the database. Committed transactions cannot be aborted because they've been already written to the database. Aborted transactions that are rolled back can be restarted at a later time. This is an example to show a state transition diagram for transactions. It was part of the worked examples for unit 4, week 4. It just shows a transaction begins, it's active for how long it takes to be active. Then it's partially committed, then finally committed to the database, or it's partially committed and aborted, meaning it failed, and then it's aborted, or it's active and it fails, and it's aborted, it failed, and it gets aborted, and it doesn't write to the database. So this is not a transaction management flowchart diagram, and we'll talk about that further a little bit later. This is just the state transition diagram for transactions. This is not a flow of what your transactions will do for your store. 4 basic properties of a transaction, they're called ACID properties that help define a transaction, are the animosity, all or nothing property. A guarantee of animosity prevents the updates to the database occurring only partially, which can cause greater problems than rejecting the whole series outright. Consistency must transform the database from one consistent state to another. Isolation, partial effects of any incomplete transaction should not be visible to other transactions. And then durability, the effects of a committed transaction are permanent and must not be lost because of a later failure. So these 4 properties apply to all transactions being done against your database. This is just a screenshot from the text that shows the database management system transaction subsystem to show all the different components that go into managing transactions within the database, starting with the transaction manager, working its way through all of these different schedulers and managers, access manager system, and finally hitting the database and system catalog. You notice that it's a two-way street all the way around. Transaction flowchart. This is what they had an example of for a transaction flowchart. This is a very poor example of what a transaction flowchart looks like. This is not a good example. It's missing proper flowchart symbols and flow of transactions. This looks like it was made in PowerPoint. You should use whatever application you use for your ER diagram. You should be able to create a flowchart using that same program to give me the flow of the transactions. And it should be a little bit more detailed than begin, partially, transaction, end. This is very bad. Concurrency control is the process that's used in managing simultaneous operations on the database without having them interfere with one another. It prevents interference when 2 or more users are accessing database simultaneously and at least one is updating the data, because your organization, small or large, you have several employees working maybe in your store, and people are doing stuff online, but you have employees working, they're all accessing your database at the same time, right? We don't want them writing data that may interfere with the data that you're writing, so that the system has to control that somehow. Although 2 transactions can be correct in themselves, interleaving those operations can produce an incorrect result. So we want to make sure every transaction stays isolated from start to finish. Two basic concurrency control techniques are locking and timestamping. Both are conservative approaches. They delay transactions in case they conflict with others. Optimistic methods assume the conflict is rare and only checks for conflicts at the commit phase. Locking is the process the transaction uses these locks to deny access to other transactions, and so it prevents incorrect updates. If for some reason you have two people working in your organization and they're trying to do different updates to some of your customer records, they open the customer record, they'll now have a lock on it to prevent somebody else from accessing that record at the same time and writing changes to that record that may affect or be interleaved with the changes that you're making. It's the most widely used approach to ensure serializability of your data. Generally, a transaction must claim a shared read or an exclusive write lock. Lock prevents another transaction from modifying that item or even reading it in some cases, in the case of a write lock. Some basic rules for locking. If a transaction has a shared lock, it can read, but it can't update. If the transaction has an exclusive lock, it can do both, read and update that item. Reads cannot conflict, so more than one transaction can hold shared locks simultaneously on the same item. There can be multiple read locks. Exclusive lock gives the transaction exclusive access to that item. So usually if you're going to update data, you probably have an exclusive lock, right? Some systems allow transactions to upgrade read locks to an exclusive lock or downgrade exclusive to a shared. There's something called two-phase locking or 2PL. It's a protocol if all locking operations proceed first, unlock operation in the transaction. So two phases of a transaction include the growing phase and a shrinking phase. In the growing phase, you acquire all your locks, but you can't release any of those locks. You release those locks during the shrinking phase of your transaction, but it can't acquire any new. So it has to go through those two phases. There's something called a cascading rollback. So if every transaction in a schedule follows this two-phase 2PL schedule is serializable. However, problems can occur with interruption of when locks can be released. So transactions conform to 2PL, T4 aborts. So since transaction 15 is dependent on transaction 14, this transaction must also be rolled back. Since transaction 16 is dependent on 15, it too must be rolled back. That's what's considered a cascading rollback. So it cascades backwards. So to prevent this with 2PL, you leave release of all the locks until the end of the transaction. One second. Deadlocks, excuse me, is an impasse that can result when two or more transactions, each waiting for locks held by the other. So this example shows when you get to this wait phase in the transaction, they're both waiting. They're both trying to write or read data from the same data, right? So balance, they're trying to deduct $10, and here they're trying to add $10 to the balance. So they both have a lock. So now we have a deadlock. We don't know which one is going to process. So they're deadlocked. There's an impasse. One way to break the deadlock is to abort one or more of the transactions. Deadlock should be transparent to the users, so the DBMS should restart transaction. However, in practice, the database management system cannot restart aborted transactions since it is unaware of the transaction logic, even if it was aware of the transaction history. So 3 general techniques for handling deadlocks are timeouts, deadlock prevention, deadlock detection and recovery. And we'll talk about each of these 3 on the next few slides. A timeout is when a transaction requests lock, it's only going to wait for a very system-defined period of time. If the lock has not been granted within that period, the lock request times out. In that case, the database management system assumes that the transaction may be deadlocked, even though it may not be. It aborts and automatically restarts that transaction, right? And then it waits for the system allocated or defined period of time again until it finally gets accepted and allowed to process. Deadlock prevention, where the database looks ahead to see if any of the transactions would cause a deadlock and never allows a deadlock to occur in the first place. You could order transaction using a transaction timestamp. They have a wait die timestamp. They have a wound wait process, right? Only older transactions can wait for younger ones. Younger transactions can wait for older ones. So it's a whole process in ordering the transactions. Recovering from deadlock detection causes several issues, which you have to choose a deadlock victim. Which transaction do we choose as the deadlock victim? How far do we have to roll this transaction back? And then how do we avoid starvation and not having any data available? We can do something with timestamping, where transactions are ordered globally. So the older transactions that have a smaller timestamp get priority in the event of a conflict. So that way you're processing them in the order that they came in, right? Conflict is resolved by rolling back and restarting transaction. There are no locks, so there's no deadlock. A timestamp is simply a unique identifier, which is created by the database management system that indicates the relative starting time, or it can also be generated by using a system clock at the time of the transaction started, or by incrementing a local counter every time a new transaction starts. So some people do it either way, but more than likely, I've seen it where it's just a timestamp. It's the actual time down to milliseconds of when the transaction started. The read write proceeds only if the last update on that data item was carried out by an older transaction. Otherwise, the transaction requesting the read write is restarted and given a new timestamp. So you have two different types of timestamps, right? There's a read timestamp. Every time a data item is read, it writes a timestamp, and every time it's written, it writes a timestamp when it was written. Database recovery in case of any failures, right? It's the process of restoring your database to a correct state in the event of a failure. You need to have recovery control in place to perform that. There's two types of storage: volatile, which is your main memory in the servers and your computer, and non-volatile. Volatile storage does not survive system crashes. If the system crashes, your memory gets erased. Stable storage represents information that's been replicated in several non-volatile storage media with independent failure modes in between. Different types of failures you could experience: system crashes resulting in loss of main memory, media failure resulting in loss of parts of secondary storage, which is why it's important you have that RAID configuration in place, application software errors or natural physical disasters, carelessness or unintentional destruction of data or facilities, and finally sabotage. With transactions and recovery, a transaction represents a very basic unit of a recovery. So the recovery manager is responsible for atomicity and durability. If failures occur between commit and database buffers being flushed to secondary storage, then to ensure durability, the recovery manager has to redo or roll forward the transaction updates. If a transaction has not committed at the failure time, the recovery manager has to undo or roll back any effects of the transaction for atomicity's sake. Remember, atomicity is all or nothing property. Partial undos, only one transaction has to be undone. Global, all the transactions have to be undone. This is an example, and a couple slides back, we'll give you the results to this questions. The database starts at time t, small time t0 here, fails at time tf, assuming data for transactions 2 and 3 has been written to secondary storage. T1 and T6 here, T1 and T6 have to be undone. In the absence of any other information, the recovery manager also has to undo T2, T3, T4, and T5. Recovery facilities. The database management system should provide the following facilities to assist you with your recovering of your system, and most database management systems have these in place already. A backup mechanism, which makes periodic backups and copies of your database. You can set a schedule and we'll do it for you automatically. A logging facility keeps track of the current state of transactions and database changes. A checkpoint facility, which enables updates to the database in progress to be made permanent. And a recovery manager, which allows the database management system to restore the database to a consistent state following any sort of system failure. Databases have what's called the log file. It contains information about all updates to the database. It keeps track of all transaction records and all checkpoint records. It's often used for other purposes, for example, auditing, because it writes to the log file every single thing is done in the database. So it's really good for auditing purposes. This transaction record contains an identifier for the transaction, the type of log record it is, whether it's a transaction to start, insert, update, delete, abort, or commit. The identifier of the data item affected by the database action, insert, delete, and update operations. There's a before image of the data and after image of the data, and then some log management information is also provided. This is an example of what a sample log file could look like, right? We have our T transaction identifier, we have our time. The time wouldn't be that simple, right? 10, 12, it would be down to probably the milliseconds. The operation, excuse me, the object in the database that was being done, it has an image of before and after, and then some pointers, some database management pointers. This log file can be duplex or triplex. Log files sometimes split into two separate random access files. Potential bottleneck. It's very critical in determining overall performance. A log file, as you could imagine, could grow exponentially large very fast if it's writing something to the log file for every single transaction that's taking place in your database. So every write, read, or whatever to the database is written to this log file. So usually the log file may be stored on a different database on a different server so that not to impact the performance of the database itself. There's something called checkpointing. A checkpoint is a point of synchronization between the database and a log file. All the buffers are force written to secondary storage. A checkpoint record is created containing identifiers of all the active transactions. When a failure occurs, it redo all the transactions that committed since the checkpoint and undoes all the transactions active at the time of crash. So in our previous example, with the checkpoint at time small tc, changes made by T2 and T3 have been written to secondary storage. So we only have to redo transactions 4 and 5 and undo transactions 1 and 6 because they were still active at the time of the failure. So different recovery techniques. If the database has been damaged, you're going to have to restore it from the last backup copy of the database and reapply updates of committed transactions using that log file, which has the before and after image, right? If the database is only inconsistent, you're going to need to undo changes that cause that inconsistency. You may also need to redo some transactions to ensure updates reach the secondary storage. Here, you do not need a backup, but can restore the database using the before and after images in that log file. So you see how important that log file is. There are 3 main recovery techniques: deferred updates, immediate updates, and shadow paging. We'll talk about each of these in the next 3 slides. Deferred updates are when updates are not written to the database until after a transaction has reached its commit point. If it fails before the commit, it will not have modified the database, so there's no undoing or changes required. It may be necessary, however, to redo updates of committed transactions, as this may affect, may not have reached the database. Immediate update is just like the name implies. Updates are applied to the database as they occur immediately. You need to redo updates of committed transactions following any failures. You may need to undo effects of transactions that have not committed, and essential that the log records are written before the write to database, write ahead log protocols in place. If there are no transaction commit records in the log, then the transaction was active at failure and has to be undone. Undo operations are performed in reverse order in which they were written to the log file. And then we have something called shadow paging, which maintains 2 different page tables on the database server during the life of the transaction: a current page and a shadow page table. When the transaction starts, these 2 pages are exactly the same. The shadow page table is never changed thereafter and is used to restore the database in the event of a failure. So during transactions, the current page table records all updates to the database. When a transaction completes, the current page table becomes a shadow page table. So it's continually rewriting itself, right, so that you always have a current picture within that table. Some different advanced transaction models. Protocols considered so far are suitable for types of transactions that arise in traditional business applications, which are characterized by the data has many types, each with small number of instances. Designs can be very large. Design is not static, but evolves through time. Updates are far-reaching, and there's cooperative engineering in place. It may result in transactions of long duration, giving rise to the following problems. So if you have transactions that are taking a long time to run, right, these updates and transactions in this database happen within milliseconds, right? They happen so fast. Long running transactions are more susceptible to failure, you need to minimize the amount of work loss. So you may access large number of data items, concurrency limited if the data is inaccessible for long periods of time. So if a transaction is taking a long time, right, it has a lock on this data and no other transactions can effectively read or change that data. That like is more likely then if you have this transaction that's taking a long time to run, and cooperation through the use of shared data items restricted by the traditional concurrency protocols. There are 5 different advanced transaction models you can look into: nested transactions, sagas, multi-level, dynamic restructuring, and workflow. We don't go into all of those are more advanced topics. So now that was a live chat portion. We'll talk about individual project 4. My website had the worked examples you should have downloaded at the start of class. Your assumptions here. You're concerned about the possibilities of losing data because your database system malfunctions or downtime. Security is also a major concern to the company because it's common knowledge that engaging in online business can be risky because of known vulnerabilities on the internet. The company also realizes that its in-store database system is your top priority at this time. So that's what you need to focus on. What solution can you propose to effectively manage database transactions, maintain security, and recover the data that may be lost from system failures or downtimes? Your assumptions are noted. A high volume of orders occurs during day. One person will serve the role of database administrator. The database administrator account will serve as the database owner. The transaction log must be backed up. A point in time recovery is required. There is an always on availability group, and the ability to purchase products online will be addressed in a future database project. So for this project, your deliverables, answer the questions, right? What solution can you propose to effectively manage database transactions, maintain security and recovery, the lost from system failure or downtime? What is your rationale for the transaction management plan, database security procedures, backup plan, and recovery model that you are going to propose for this case study organization? Create your deliverable 4 to 5 pages. Create a database administration plan that's specific to the needs of your retail store. Include with that a transaction management plan that includes a flow chart. So you need to define your transaction management plan, and you need to include a flow chart that shows how each transaction will be handled, including a rollback and commit cases. Make sure you have a specific block on there that has rollback and one for commit if your transactions fail or if they're successful. Do not find a flowchart on the internet and put it into your paper. You have to create your own for your specific store. So do not find one on the internet to put it in your paper, even though you may think it's easier. You need to create one for your store. And I have an example at the end of the PowerPoint slide. Include a database security procedures that involves provisions for access control, user authentication, and availability. It's not good to simply tell me you have database security procedures in place and that you're going to control access, user authentication, and availability. I want to know specifically how you're going to do that. Also, I need to know exactly what your backup plan and recovery model are. How are you going to back up the data? How often are you going to back up the data? What database backup model are you going to use? And what recovery model are you going to use in case of failure when we have to recover the data? And then, of course, provide your analysis on how this part of the project fulfills the mission, one or more goals of your store. There's a link in the PowerPoint slide that you can get from my website, which shows you how to create a basic flow chart in Visio. If you have Visio, there are literally hundreds of resources available for how to build a flow chart. I Googled how do I create a flow chart, and that's how I found that one. Of course, you have to cite both in text, your references in APA format. You know how to name your documents by now. This is a good example of what a transaction management flow chart looks like. This one, however, is deficient in the fact, it has a commit, finalized transaction, commit to database. I'm not sure if it has the rollback segment. If it doesn't, it needs to. So this is what your diagram should look something like this. You don't need to necessarily have that big green thing in the top that explains what it is. Just create the flow of your transaction through your system from start to finish. So you notice this has valid flowchart symbols on it with decision symbols and process flows. So go ahead and do it that way. You can email me or message me with any questions or comments or concerns you might have on any of the projects. Again, you have my email address. Our live chats and my office hours are listed, and those are the references. So that concludes our live chat for this evening. If you have any questions or need any help, please feel free to reach out at any time, and I'm more than happy to work with you and help you work through any issues you may be facing. I hope you have a wonderful evening, and we'll talk to you next week for our final live chat for week 5. Thanks and take care.